Perfect. So look, I'll kick off. If anyone else is joining, they can catch us later. So for everyone who has joined, first off, thank you. I really do appreciate it. I know previously just saying before to Junli and Carlos, we've kind of hit an end of what will probably be the webinar series of computer vision in production. And going forward, I will look to hopefully do as many webinars in person or meetups in person as I can, with looking at recording them for audio and for video, maybe sharing them through the computer vision channel, podcast channel, and also onto the YouTube channel then as well, so that we can still make sure that if I'm hosting it in Berlin and you're in Austria or you're in Ireland or wherever you may be, you will still be able to get access to that content. And then I suppose, look, for anyone who doesn't know me, my name's Anthony Kelly. I'm the founder of the computer vision and production community. And my reasoning behind it is I wanted to create a place for computer vision professionals to connect, share information, successes and wins about some of the work that they're doing, because a lot of the approaches that you guys are working on are very novel, very innovative, and it's often very hard to have conversations when you come home after a long day and someone asks you, hey, how was your day? And you tell them, hey, I have no idea. This computer vision model wasn't working. In many cases, a lot of people don't even know what computer vision is. When you start telling them about your UNets and your and your CNNs that just aren't working right. But I'm also a computer vision recruitment consultant with Trust in Soda. And our guests for this afternoon and our guest speakers is Junli, who's a computer vision engineer at Virtual Retail. Junli will speak about vision transformer networks and their applications in classification, object detection, and segmentation tasks. And then we've got Carlos, who is also a senior computer vision engineer currently with Oxolo. Carlos has a fantastic presentation lined up for us here as well, which is on GAN-based data augmentation for face recognition. Um, I mean, there's no one else better to give themselves their own introduction. So Junli, I'll let you take it from here. You can share your screen if you can introduce yourself and say hello to everyone, and best of luck with your presentation.
Thanks, Anthony. Let's see whether the screen sharing actually works. Now, hopefully you see the slides.
Yes, we can see it. Sorry.
Cool. Thanks for the feedback. Yes, a bit introduction about myself. I'm Junli. I did my PhD in University of Auckland in New Zealand, and that's in 2015. During my PhD, my topic was vision-based object tracking, and their objects were vehicles, pedestrian, and fruit flies. And I had a chance to go to Daimler to do an internship there. So we did vehicle detection on highways, a small project. And before I graduate, we did an interesting project with AUT. They having a drone flying over the Antarctica area. So they want to investigate the vegetation on Antarctica. So I'm helping them to analyze the videos. After I graduate, joined Crown. There we do autonomous forklifts. So this project involves 3D feature and construction, sensor fusion, mapping, and localization. So after a couple of years, I find I need some new tasks and new challenges to do. So I joined Virtual Retail in 2019. Here we do various projects. We have the body modeling. We also, that means we're using the 2D images to measure the body measurement to kind of give size recommendation. Another project is the industry project, which we detect hands. So we can help with the worker in the warehouse to pack the products. And also there is a medical project coming up. And we are hiring. So if you're interested, checking our LinkedIn page, the company page with the job, JD. So this link I can send this link to the chat later on as well, if you're interested. So today, unfortunately, I'm not going to talk about any project on VR. I'm going to talk about the transformers for vision tasks. And to start with, I'm not gonna cover all the papers about transformer. I think that's impossible in 30 minutes. So I just picked some that are relevant and of our interest. So why transformer? A short answer is it can model long dependencies. So transformer is initially introduced in an MPL. And the so with MPL, you normally have, for example, you have such a sentence like the animal didn't cross the street because it was too tired, and the it is referring to the animal. With RNN, recurrent neural network, and you can also do this, and you can also encode this information, but because the way it is encoding this in a sequential way, because the distance between the animal and it is a bit long. So when the information propagates through this network, it is missing the information, and it's not good for this kind of long-term dependency encoding. The LSTM is introducing a few gate functions to improve the dependency performance, but it is still limited. So that's where the transformer comes in. On the left side, this is the kind of overall structure of the transformer. It takes the whole sentence as input instead of taking one word at each time. So we have the full structure of the sentence. And it have this encoder blocks and also decoder blocks. For this case is a translation task. So with the encoder, when it's encoding each word as a feature representation, it will consider the other words in the sentence as well while it's doing the encoding. So at the end, those feature encoded will be passed through to the decoder for the translation job here. And for inside of the encoder and decoder, it is a self-attention block and a forward network, basically MLP. And with the decoder, you still have the same structure, but there is a new encoder-decoder attention. So this part is combining the encoder with the decoder information altogether. And the special thing about transformer is the self-attention module. So what it is, on the right side here, given the input, which is a word, we also call this a token. And then you first embed this word into a numeric vector, because the computer has to understand that, right? And then with this input, we will multiply the input with this weight matrix, the weight matrices, the WQ, K, and V. So this weight matrix, you can consider them as the convolutional kernel weight in the CNNs. So this is going to be learned during the training procedure. So after multiply this, you will get a feature representation, not a really feature representation. In this case, you will get a query, a key, and a value vector for each token. In this case, it will be Q1, Q2. We only have 2 here. After you got this, then you calculate the weight value for each of those tokens and weight the value and sum them together. So this is basically a Z. Now we try to get the feature representation Z for the thinking word, and we are considering the the effect of machine for this thinking word to be encoded. So this is the attention mechanism that is really the key part of the transformer. So instead of using one set of attention, like one set of WQKV, often there is a multi-head, they call it, multi-head self-attention. So you have multiple set of attention weights here. At the end, you will have multiple features, and there is another weight function, weight matrix WO need to be learned as well to combine those feature vector into a single one. So one thing to be pointed out is The dimension of the weight matrix will grow exponentially according to your input feature vector or the embedding vector and the output feature vector dimension. So this is, a lot of people talk about like transformer could be really memory greedy when you have a large input feature embedding. And you also want a relatively large embedding to represent that input feature, then this dimension kind of expands the memory. Then you need a large RAM GPU to do the training. And that's one of the hindsight as well, if you want to work on this model. So that's a cap about the MPL aerial transformer. So with VIT, the vision transformer, this is the first paper proposed. It takes the image and first split the image into small patches. And each patch here is corresponding to a word. This is a one token. And before it's passed through the encoder, they will do a flatten. So they will straighten this 2D patch to 1D and then do a few MPL linear projection layers, and then you get a feature representation. And then you add the feature embedding into each of the feature. In this case, basically you have 9 patches here, and it's just give the number to distinguish which patch is where and the corresponding space correlation. The important part is about the class token here. So talk about if you embed it during the encoder, each feature embedding will be considering all the rest other features as well. So this class token introduced here is for the classification task. While we're training, we will be able to say, okay, now during the training, please look at the rest of the image patch to decide which class it is. Then at the end, you only need a few MLP layers to perform the classification task on top of the class token. So inside this encoder, we will have the very similar structure as the MLP transformer, normalization, multiple head, and then MLP. So also they have some residual modules as well, which is quite standard. So here, if we have, again, a large resolution image, then this transformer encoder, the weight matrix will be really big as well. So this poses the difficulties of training such a large model with the memory limitation. And also because the transformer basically don't have any prior, like with the convolution neural network, you will have the prior, say, I only look at the local regions that the feature is important. But with the transformer, it says just look at the whole image, pick wherever it's important. So there's less prior encoded into this framework. And generally this requires a larger, much larger data set to train this to get a reasonable performance. So that said, which is not ideal for some small data set and with limited resource. So this paper, DEIT, which introduced a distillation token, which the rest of the framework is exactly the same as VIT, but it introduced an extra distillation token. So to kind of, it's basically a distillation concept that you have a teacher network, and this teacher network will be producing the results for this loss calculation. And you still have the normal ground truth calculation for the cross entropy loss here. And with this, interestingly, it improved the performance quite a bit. And also in their experiment, they find with transformer, the hard distillation works better than the soft distillation, which is the other way around in convolution neural networks, which is quite interesting. Also, they actually did a few tests with the augmentation method, which is quite common in CNN, and also regularization. But the two things, the dropout and exponential moving average, which works quite well in convolution neural network, didn't really bring much to transformer, interestingly. And also another factor, if you want to train a high resolution input image, which we said that's going to be really expensive for the, really demanding for the memory, you can do a small resolution training and then fine tune it with a larger resolution. So this might save you some cost if you do cloud training. So that said, there are people actually working on how to improve the augmentation and some other techniques to improve the performance of transformer. This paper proposed something quite intuitive and simple, but achieved relatively good results compared to the other paper, which is using a whole lot of GAN-based method. So one of the things they introduced is the mixed token. It's illustrated here. So basically, because the input is not just the image as a whole, we split the image and then fit to the network. So with this procedure, if you use the normal cut mix, you will end up with some patches having the content from different images, which is not ideal. So you just do the split first, and then you do the cut mix. Yeah, very simple, but it works well. Here, this chart is a good overview about a lot of papers. Here, this model size, VIT, is basically the baseline, is large and is the least accurate ones. And the DIT in this paper, if you only do distillation with the same size, it improves the performance, which is proved the same thing as in CN as well. So distillation is really a good way to boost the performance. There are heaps of other papers we actually skipped, we didn't mention today, but there is another one called Swing Transformer. This is Swing Transformer Tiny, which is a smaller model, but performs relatively good. There is a larger model which performs well, but it's not in this chart. So swing transformers, in the VIT, for each encoder, the token is the same. It still be the same size, and each token is attending to each other token in the whole image. So that's not that's kind of the way you don't have any pyramid structure like you will have the fine or coarser scale, etc., like used in CN as a backbone. So with swing transformer, they introduced a window-based self-attention. So with the first block here, you take the image and you split this image into small windows, like the red rectangle here. And inside each window, then you will split the image, the sub image to patches, like the little gray boxes here. So this little gray box is a token, and the attention is only happening inside each window. So you're kind of constraining, say at the beginning, you don't look at the whole image, you only look at the local, which is not as local as CNN, but relatively small scope compared to the whole image. And the second layer, then you will merge those windows to be a bigger one. So you get a larger attention area that they can attend to each other. And gradually you get an even larger one. So this kind of provide a feature backbone. It's similar to CNN, which is really convenient that you can swap any convolution neural network backbone with this swing transformer, for example, for object detection, segmentation tasks. So this is a bit more detailed structure of the swing transformer. So we take the image, the same deal, linear embedding, and then the swing transform block, let's ignore that for now, and you do the patch merging, and you stack this for a few times. So what's special about the swing transformer block on the right side is the detailed one. So the embedding comes in, we do linear would do the layer normalization. That's the same thing. And they are not doing the normal self-attention. They are using a window, a multi-head self-attention that we talked about with a little window. And they still have the same residual and MLP layers. But also they're having a second part, which is very similar, but with a shifted window multi-head attention. So what is this shifted window thing? In the first block, like this window, MSA is basically that you calculate only attention inside this window, each of them. And on the second part, you will shift the window, for this case, to the 2 blocks to the bottom, to the bottom and right side. And you end up with a window like this, splitting like this. This is not ideal. You have different size and it's not efficient to calculate. So they introduce with a window partition, you basically moving the top few patch and just pat them to the bottom right corner. But because those patch are not originally from here, so you introduce a mask to just calculate, when you're calculating the attention, you just calculating the gray part, you ignore the colored patch here. So this make it really efficient to calculate as well. And it is tested with classification, detection, and segmentation task. Each of this were, I think when they first proposed, was leading this benchmark for quite some time. Here is the interesting ablation study they did. So if you do it without the window shifting, it is kind of much worse if you look at here. So this shifting window technique is really improving the performance. And here they also tried out a few different embedding position embedding techniques to kind of test out which one works better. As said, transformer often require a large data set, and labeling a large data set is always challenging. So they are papers try to use self-supervised training to train transformers. And this Dino is one of the paper, I guess some of you probably heard about this. You use the input, you augment the input to 2 version and pass through the network, ideally the same one theoretically, but they're using different one for this case. So, and then at the end, because they are the same image, the results should be as close as possible. So because they want to avoid model collapse, which is the often case for self-supervised training, they are using exponential moving average weights from the student to move to the teacher. And also they introduce a centering, which is basically subtract the mean of the feature, the feature you get out of this model. Yeah, too much in detail, I guess. Skip that. So here are some results, not really results. Here are some attention maps. So the second column here, you will see different color code. Each color is representing one self-attention head produced attention. So on the right side is also the same thing, but this is just different color coding. So it's already giving you quite good details about the object in the scene. And also they did an interesting comparison. If you train the transformer with a self-supervised learning technique, or you can train this with a traditional supervised way. So the attention maps are quite already telling that the self-supervised training is learning the fine details of the silhouette of the objects quite well. And based on this, there is already potential that you can do segmentation without detailed label of your data. So it's really a powerful thing that combines the transformer with the self-supervised training. Jumping through to the application. So in VR, we're doing detection. DETR is the one of the paper that use transformer to do detection. It's using CNN to encode the feature and then add embedding. It's exactly the same as the MLP transformer, but the different part is the object query here is, for example, if you assume that we will have 50 objects in the image, you will give 50 queries. Each query will be like 5 digits vector. You will have one class vector and 3 numbers for the box location. So, and the insight is also the same. This works reasonably okay, but is by far not as good as CNN or YOLO family performance. So it is not the way to go yet. And another thing we're doing I talk about we having a project. We do take the phone to take picture of a person with the RGB image, and then we estimate the body measurement, like the baskets, the length of the inseam, the length of the arm, etc. Those measurements. So we do the size recommendation on top of that. And transformer is introduced for in this paper. They don't rely on any parameterized 3D mesh like SMPL. Basically, what they do is you take the input image, you encode this with CNN, get a feature vector, and you take a template mesh, which will be joints and vertices. Then you encode the location of each joint with the same feature vector you get from the image. And this position encoding done, and then you pass this through into the encoder. And what you get output is the 3D location of each joint and each vertex of this template. And then you will have a 3D mesh at the end. Very simple end-to-end method for this task. And it works actually quite well. If you can see on the right side is the overlaid mesh of the 2D person on the 2D image regarding the person. It's not like perfect for sure, but with such low guidance, it is really impressive results achieved. And also here they show the attention for each, for example, like here they illustrated a joint like right wrist. So the bright lines are the attention connections of this target location corresponding to other vertices, which kind of makes sense, but the limb seems to giving much more attention to most of the joint location. With this, one thing they did mention is about the training time. I foresee, so normally with a template mesh, I think you were expecting 2,500 vertices at least. So this token line, this token input would be really massive, and also depend on how the feature vector here, the dimension is. So this network could be huge and it's gonna take ages to train. But yeah, it's good that this idea, I mean, at least the concept works. We are having a medical project coming up, which is not related to the segmentation task, but just for interest here, we list one medical trans unit network here. Basically, it is still the same procedure. If you can ignore the transformer part, then it will be a UNet. What this transformer layer here does is basically try to encode the high context level structure a bit better, which leads to a bit better results. Yeah, interesting way to apply it. Of course, this is not full list. There's also some other papers I will just not list them here and not mentioning. One last thing though, transformer is not the only direction to go. So while everybody excited about transformer being so powerful, there's still one direction of researcher who is looking into a more generalized framework, like only MLP, only a few stacked together MLP layers, how that works. So this is very simple structure. You take the input and you get the feature representation and you flip it, and then you do another MLP and you flip back again MLP. So basically it's pure MLP layers. And if you look on the right side, the VIT, those dash lines are the VIT results, and the solid lines are the MLP results. While at the beginning, when the training set is relatively small, the performance is the performance of the VIT is better constantly. While the image set is getting larger, they are like converging together. But I think this 300 million data set, which is not publicly available at the moment, is only, I think it's Google. Yeah. And this is the point, feels like the MLP is about to getting better performance, but unfortunately, we're not able to see whether this is actually the case. If we have a larger data set and we can see these lines keep going up, then probably we can conclude that more generalized model with a larger data set will be more powerful. But I think we still couldn't conclude that. To list this paper here is just to say, like, transformer is not the only way to do it. And at the end, we are hiring. So if you're interested, get in touch. Yeah, that's my talk.
Excellent, Junli. Thank you. I really appreciate it. That was absolutely fantastic, very insightful. I suppose if anyone has any questions, you can ask the questions in the Q&A box. You can raise your hand, and I can open you to talk if you have anything you'd like to ask to Junli about her presentation, maybe even about the opportunity she mentioned. Cool. Last call for a question from anyone. Oh, here we go. Nice question here from Alexander Junli. He says, thank you. Nice talk. He said, MLPs are fun, but the real question is, why do you use transformers instead of CNNs?
I'm a fond of transformer, but I'm not sure this is the way to go at the moment. So to be clear, we are not using transformer in our production line. This is only something we feel like it's an interesting area we keep an eye on. There are good things about transformer. It depends on what kind of task you want to do. So with the, as I show with the self-supervised learning with transformer, it is already able to learn very good detailed heat map or attention map already. So you can do segmentation task without labeling all your data set, which is gives the potential that you can perform in such a task without labeling. But for our case, we want to have efficient real-time, more like accurate model. So this is not what we're using.
Excellent. And a follow-up question quite links well to the one just asked by Alexander from Christian Benz. Again, thank you for the nice talk. He says, how about training times? Are transformers harder or longer to train than CNNs?
I think this is not a yes or no question. It depends on what kind of CNN we talk about, right? You can have a massive CNN models, like very deep. But in general, if you want to performing for example, a task, say face recognition, depend on how many people in your database you need to recognize. If you have only 20 people and you don't really need to have this fine-grained details to separate them with a grade level, then you will just require a base, maybe ResNet 50, even less, ResNet 18 will be working fine with it. In those cases, definitely CNN will be much better compared to Transformer. So it kind of depends on your use cases. But in general, yes, with comparable performance, Transformer takes a bit more time and memory to train in general.
Excellent. Junli, thank you for that. I really appreciate it. And look, up next we have Carlos. Carlos, if you're ready to turn on your camera, share your screen, introduce yourself, and get into it. Thank you again, Junli. I appreciate it. Fantastic.
No problem.
If you can stop the sharing, Junli, please. I'll start sharing mine.
Sorry.
No problem. Thank you so much. So let's start with it. So I will introduce myself in 30 seconds. My name is Carlos Fernandez, and well, I purchased my PhD on Autonomous University of Barcelona. I was working on behavior understanding in complex video surveillance scenes. I participated in some FP6, FP7 projects back then. Then I went to a private company. I have worked in airtime security for almost 11 years. I started there working as a research intern. I went to director of research, and then I became CTO. And well, we have been doing face recognition in very unconstrained scenarios with many high resolution streams simultaneously analyzed and really difficult, challenging scenarios. And this work that I will present actually belongs to that time. It's some work that we started 2 years ago and we concluded some months ago. And well, after that, now I just recently joined another company, a remote company called Oxolo, brilliant company. Later, I will also share some hiring information because we are still hiring for some junior, senior ML engineers, management positions, sales positions, and Unity developers. I will share that later. Okay, let's go ahead. First, to say that this work has been done together with Sergio Montoya, which was the PhD student that I was supervising at the time. I want to mention that. So let's get into it. Let's get into the context of deep face recognition in the year 2019, which was the year where we started that project, right? So this is the typical, let's say, pipeline for face recognition in a video surveillance environment. We have different stages. At the beginning, we have to detect the faces, localize fiducial markers so that we can align the face properly. And then when we collect enough data, let's say millions of images to have a proper face recognition state-of-the-art model, then we use a backbone CNN, which is used for feature extraction. And we use any classifier. It may be a softmax classifier, it may be an arc-based classifier, such as arc face or sphere face, something like that. And once we had that, we have converted the input image into an embedded feature, facial feature, which we use to, let's say, encode the identity of the face in the superspace of the feature, maybe 256 values, something like that. And then, well, we tag each of these features for all the subjects that we have there, and we train this model. Then at different time, we have a couple of images, a pair of images. One of them is the image that we have registered into the gallery. It can be more than one, but minimum is one. And then we have the image that we are acquiring at a specific frame from the camera, from the IP camera. Then we run the train backbone that we are not changing anymore. And that backbone is, again, transforming the input image into a feature vector. And we compute the feature distance between these two vectors, typically L2 distance. And then we know how far or close they are, right? Then we threshold it and we know we have to raise an alarm or not. This is how it works for face recognition. Everything is beautiful, but we have a problem. Although the training datasets are very large, in the order of tens of millions of images, they are not enough diverse. So the diversity is a problem in face recognition. We usually tend to use images of celebrities because they are everywhere. We have a lot of imagery there. But the problem with celebrities is that mainly they are looking happy or neutral. We don't have many faces with variety of attributes like glasses, like different expressions that are not happiness. Most of the celebrities are always looking happy in the magazines, or neutral. So we have, you can see here that for the main large data sets like BGG, IMDb, MSL1M, we have a lot of happy and smiley images. But for instance, that became a problem last year, and when we went into pandemics and suddenly everybody was wearing masks, and we don't have images of masks. Luckily for us, masks are quite easily to reproduce, just occluding parts, but we have a problem with attributes, right? We don't have a lot of attributes and a lot of variety. They are very biased on some specific attributes. So what can we do? The idea and the proposal is to synthesize new appearances using GANs, using image-to-image translation. Then instead of one aligned face, we can have different poses, maybe different expressions, different presence of glasses, non-glasses, so that we can, let's say, tell the model which kind of images it can be possible to receive, and have it, let's say, more aware of possible variations of the input images. All right. This is the idea. Some considerations before we went into that. For the business case that we were having, first of all, we were thinking of multiple attributes, as we said, like different emotions, different expressions of the face, different presence of glasses or not, different presence of mask or not, maybe. And also the problem is that we have unsupervised images, unsupervised environment. What does it mean? That we don't have the pairs of every image. We don't have a person with and without glasses all the time. We don't have a person with a fearful expression or a happy expression all the time. Sometimes we have one, sometimes we have another, and we don't have the other one. So also with glasses, gender, well, we don't have the opposite gender of a person. We have to synthesize it, but we really don't have it at the beginning. Then other consideration, some attributes are actually ill-posed for identification. We want to generate images keeping the same identity for that person, but that's ill-posed for gender and ethnicity. If we just convert one person from white to black or black to Asian, we are actually changing the identity. And the same for gender. If we convert one woman to a man or the other way around, we are actually modifying the identity. So this is kind of ill-posed also. We have to play with that. Another constraint is that we need real time. We're working in video surveillance, so we want to do that in real time. And another final consideration is that we're working in a real life environment. We have very, very unconstrained samples, as I said. These are actually examples from 1 month ago from a real project. I just grabbed the images from a mall, and these were the kind of images that we were having. And as you can see, well, we have very, very unconstrained images. Sometimes 80% of the face is actually occluded, and we still have to do face recognition with that. And not only occlusions, we have illumination, head pose rotations, expressions, many different things that we have to deal with. So let's review the standard GAN formulation. I'm sure that all of you at least know a little bit the concept of it, but let's review it. So GAN is actually posed as a two-player minimax game. We have two players, which is the generator and the discriminator. The generator is this blue trapezoid that I'm having here, and the discriminator is the yellow trapezoid that I'm having at the end, okay? So the generator is actually generating from a noise sample. It's sampling a noise sample, and from that, it's generating an image that it's trying to get more and more realistic over the training, to be able to fake, to cheat the discriminator. And the discriminator is actually a simple classifier, which is trying to distinguish if an image that it's given to it, it's either really coming from a real distribution or from a synthetic distribution. So there are two, let's say, distributions: the distribution of real images, the distribution of synthetic images, and the discriminator have to guess which one is coming from. So this is the objective of the standard GAN as it was initially formulated. And in here, we have to think that the generator is trying to, let's say, assign a 1 to the images that come from the real distribution and a 0 to the images coming from the synthetic distribution. And the generator is actually trying to cheat the discriminator by doing the opposite, trying that the discriminator gives a 1 to the fake images, okay? That is why this is a confronting game between the two. And actually, that's why it's called adversarial, right? They are one fighting against the other. And then we have a variation of that formulation, which is for the conditional GAN. In this case, we have pairs of images. We have images that are paired with attributes, and these attributes are actually conditioning the presence of some characteristic in the image. And then the discriminator can actually classify that attribute, and the generator can synthesize the image conditioned to that attribute. For instance, I can say, I want an image conditioned to having glasses, and then I will generate an image that has maybe glasses. And the discriminator also has to learn to predict that the image has glasses. Okay, so these are the images that the kind of GANs that we are going to work with, the conditional GANs. And here we move to the field of image-to-image translation, which is a little bit different from the standard GAN formulation. You know that the standard GAN formulation, we are sampling from noise, but here actually the input to the generator is not noise, but it's an image. Here we have examples for cycle GAN and for peaks-to-peaks, which actually associate input images to segmentation maps, to edges, sketches, styles like night, or day, or winter or summer. And we can actually convert or affect the style of an image just by telling which is the style that we want to get. Then we have another field inside image-to-image, which is the multi-domain translator. In this subfield, we have a unique generator for all trained domains, as is the case for Stargand v2. We have here an image of a cat, and then we have different styles, different domains, okay? And each of these is a domain. For instance, we have the domains of tigers, of cats. Again, we are moving from cat to cat. And we have the domain of dogs. And here you can see that we have different styles for each domain. We can have this type of tiger, that other type of tiger, or cat, let's say, this type of dog, this other type of dog. So we can affect the style inside the domain. And then finally, we have multi-label translation, which is actually more generic. We can say that it translates at attribute level. And we have this kind of labels like which is the color of the hair, which is the gender, which is the ethnicity, that can actually be combined. So we can say, I want this input to be older, and I want it to be a male, and I want it to be, I don't know, with black hair. And then this single generator translates to all these attributes and embeds all these attributes in the final generation of the image, okay? And well, at the time of the project, we chose these architectures, Stargand, Smith, which are both multi-domain, multi-label, translation, and Stargand v2, which is a multi-domain translation. So they are a bit different. We will review them right now. So Stargand was one of the first to appear. It appeared in 2018. It has a single generator and discriminator for all the available domains, as we have mentioned, because it's as we have seen, Stargand is a multi-label translation, okay? And still, this single generator and discriminator learns a deterministic mapping for each of the domains implied, okay? So here, first, we tell which attribute we want to synthesize, and we do that with these channels that we are appending to the original image, okay? We concatenate the images and these labels, which are kind of one hot encoding, but at channel level. The whole channel is either zeros or ones, and we use it to tell the generator how to synthesize. Then the generator is this UNet that you can see here. It has the usual things that we have been seeing in UNets as they have evolved over time for generating images. So it has like these skip layers and subpixel shuffles and transpose convolutions in the upsampling and so on. And after that, we have the discriminator. So we synthesize the image, and we pass the synthesized images and also the original images to the discriminator. And the discriminator is actually having to guess if the image is real or fake. The discriminator is helping the generator to synthesize realistic images. Why do we do that? Because of the adversarial loss. The adversarial loss is actually backpropagating. This loss is being backpropagated, and this loss is affecting both the discriminator and the generator. So it's actually helping the generator to be told if the synthesis was good enough to cheat the discriminator or not. Okay. Then we also have the predicted attributes. The predicted attributes are learned by the discriminator, and then we have two losses here. One is the classification loss for the generator, which is actually, here we have. So the discriminator, as we said, predicts image attributes. It helps the generator to synthesize them by this classification loss for the generator, okay? So since we have the ground truth, well, we have the guess of the predicted attributes by the discriminator, we use this to backpropagate to the generator and told, hey, this attribute was well generated or not, or you should try a bit harder to generate well this attribute. And also, at the same time, these predicted attributes are conditioned to this classification loss for the discriminator. And this is helping actually the discriminator to learn how to predict correctly the attributes. So this is another loss. And finally, we have another final loss, which is the cycle consistency loss. How does it work? This works by, well, we have the original image, we have synthesized the image, and then what we are doing is just synthesizing again the original image by telling the generator to take this synthesized image and the channels with the labels all with zeros. Okay, then we are telling just suppress the label that you have generated and come back to the original image. Then we use this cycle consistency loss, which is based on L1 loss difference typically, and we use it to try to get the original image as close as possible. And if this is too different, then this is penalized because we should be able to convert back to the domain again. And this helps the generator to actually do a better work at domain. Okay, so this is Stargand. Then we have Smith, which is a little bit different. Smith was introduced in 2019, and we see that it's also a conditional GAN because the discriminator also predicts the attributes. They are not concatenated in this case, as it was the case for Stargand. We were concatenating these channels. In this case, we are injecting them, and the attributes are injected with a normalization technique, which is called add-in, which is actually embedding these target attributes inside within the residual blocks. Okay, so we are having these target attributes, and we are also having a style. The style is actually sampled from a noise distribution, and we are just letting the generator choose how to sample this style to synthesize the image. Then finally, we also have a mask here. Well, we have said also that the discriminator also predicts attributes. And we have the final image of the generator. Actually, it's using a mask module. How does this mask module work? So the mask actually, it's kind of telling the generator where to attend to. So we have a subregion of the image, which is the one that we are synthesizing. And the final image of the generator is actually using this masked region, the one that we are attending to, plus the non-masked region from the original image. So the original image, some part here in this case, for instance, with the glasses, it's very easy to know that we have a mask around the eyes, and these glasses are generated only in this mask. And then for the rest of the face, the original image is taken, okay? So regarding the different losses, we have, apart from the adversarial loss, which by the way is a bit different than the original formulation in the original GAN paper, we have the classification loss for the generator and discriminator, as we said before. We said we have the cycle consistency loss, and we also have a recovery loss that you can see down here, okay, which is actually trying to keep the same image, the unchanged image, when we are embedding the original attributes into the residual blocks. Okay, so we have the original attributes, we have the original image, we should have the original image as an output. And this is what this recovery loss, which is sometimes called identity loss, is doing. Okay, then we have finally a mask loss, which is affecting the mask, which is basically also called attentional loss in the paper. It's trying to make this region as small as possible so that we don't propagate over the whole image. All right, and then this is the last architecture, I promise, is the Stargand V2, already introduced in 2020. Here we see some difference with respect to Smith. Here there is no target attribute as it was here. Why? Because as we said, this is a multi-domain translation. It's not a multi-label translation. And then we actually have to tell explicitly which is the attribute to generate. So we have here this multi-layer perceptron, which is used to obtain the normalization parameters. And we are actually selecting the output of the MLP and the discriminator based on the target domain. So if we want to generate an image with glasses, we have to tell the MLP, hey, this is going to be generating glasses. And we have to tell the discriminator also, take the output with the glasses only, just don't care about the other ones because they are not relevant for this case, okay? Then finally, apart from that, also we train an encoder, a style encoder with Stargand v2, which is actually used to recover the noise vector. This is the vector that we have used here, embedding it into the MLP, into the multi-layer perceptron, and into the residual blocks. This one is the one telling us which style to get. And we actually need to recover that style for several purposes. So this style encoder is also trained in parallel to be able to recover that style, that input to the multi-layer perceptron, and that latent vector that we have used to encode the style, okay? So these are the architecture, and the enhancements that we did was incorporating 2 additional losses. One, it's called the face recognition identity loss. I don't want to say identity because sometimes there is this identity loss, single one, but this is related to face recognition. So what we want here is that the identity of the person in the synthesized image, it's very much similar or almost identical to the one of the original image, okay? How do we do that? Well, we use a trained template extractor, like a good face recognition model, to extract the face recognition templates that are encoding the identity. And then we are just comparing the distance between them with an identity loss, which is basically an L2 or a cosine distance between these vectors, okay? So this is one of them. And another one is a triple consistency loss. We have seen the cycle consistency loss, which meant to go to the style and come back again to the original. This is slightly different. Here we are generating an image of a particular domain, and then from that domain generating to another domain. And then also simultaneously, we are generating from the original domain to the second domain directly. And then we are comparing these two. This triple consistency loss is the same as the other pixel to pixel losses. Usually it's a L1 pixel difference among them. And it's very interesting to stabilize also the generator. Okay, so this is the 2 additional losses that we have incorporated to the models. And then, well, here are the results. First of all, we have to say that it's quite difficult to find evaluation metrics for GANs, because actually we don't have pairs of images. So we have to try to understand, first of all, how well the attributes are preserved. So we have classifiers that are trained for identifying attributes like glasses, like beers, like emotions, like these kind of things. So we can detect that, how well have we done. And second, we can detect how realistic are the images. And for that, well, there are a couple of metrics that we will show later. So first of all, we want to know if the identity loss helps preserving also the ID without degrading attribute generation. That is our goal. So actually, we do have a better identity preservation. Here you can see drop curves in logarithmic scale in some range, which is 10 to the power of -3 to 10 to the power of -4, which is very typical for face recognition applications in video surveillance. So in these drop curves, you have the orange one, orange yellow one, is the one without identity loss, without face recognition identity loss. And the one with green color is the one with actually trained with identity loss. You can see here that the change when we add this identity loss is quite prominent. It goes like 10%, 15% in some cases. In this one of Stargand v2, you may not see the yellow one, but because the yellow one is at 0. That means that Stargand v2 was originally destroying the identity of that person. And with this identity loss, we arrived to a very, very good, much better metric. And finally, we compare it with the attribute degradation. Here, these curves are for different attributes measured on the generated images. And you can see that the loss of attribute in the drop curve is much smaller than the part that we have gained in identity. So it should be like that, like the identity preserving improvement should be much better than the loss in attribute degradation, let's see. And this is the case, so this one has worked so far. Now, regarding realism, there is 2 typical metrics that are used for GAN for measuring how realistic are the images. One is the Fréchet inception distance, And the other one is the precision and recall of the distributions, of the real and synthetic distributions. So in the case of Frechet inception distance, we can see here that they are mostly similar. We're using the triple consistency loss and without using it. But at sunglasses, you can see that we improve quite a lot. There is 5 points less of FID. And in the other case, with precision recall of the distributions of the synthetic and real distributions, we see that we have better precision in general. So it's also satisfactory at this point. Then here are some visual results, things to show here. You can see that in Stargand, the sunglasses are actually not very successful sometimes. The ethnicity is not working so well. But for instance, Smith is much better at glasses generation thanks to this masked region attentional map, let's say. And second, Stargand V2 is actually quite better at ethnicity. And you can see that probably that's why the identity was quite destroyed by Stargand V2, because it was actually wanted to create a very new design for the style. And by putting this identity constraint, we have at least managed to keep the identity a little bit more than in the original formulation of the Stargand V2. Then, well, here's a little video of my student, of Sergio. This is the results for Stargand. You can see that the eyeglasses are not very, very satisfactory. As we were telling, the sunglasses are actually looking like weird makeup. But, well, the expressions are okay-ish. If we move a bit further, let's go to Smith. Here it goes. So for Smith, the glasses are actually much better, working in real time and not bad with different styles. Okay. The expressions are also a bit better. We can go again to a bit further to see all black. Well, this black ethnicity, Asian ethnicity is not bad, but it's quite better in the case of Stargand V2 that we will see right now. So Stargand V2, you know that we have only partial results because, of course, it's a multi-domain. It's not multi-label. So we have to train explicitly for each one of the domains that we want to go to. The classes are not bad, but they are still conditioning a little bit, affecting a bit the identity. So probably it's better to use Smith for glasses, but for the ethnicity, the results are quite satisfactory. Like we have the black one is affecting still identity, but the results are much more realistic. So it's quite interesting, the result for Stargand V2, especially for ethnicity. Okay. And well, that's it for it. I just want to remind that in my current company, in Oxolo, we are building a platform for AI-based entertainment. We are using a lot of generative models this time. We were not using them that much at ERTA, but here is very much about synthesizing really nice, realistic characters. And we are searching for a lot of profiles regarding NLP, TTS, not anymore computer vision, but we are searching for CTO and management positions and also for Unity developers. So you can check this webpage if you are interested. And nothing else. Thank you for your attention, and I will be answering any questions that you may have.
Excellent, Carlos. Well done. Really appreciate it. Really insightful as well. Really nice introduction into GANs. So yeah, so we're open for a bit of Q&A. If anyone has any questions, again, either raise your hand in the chat, or you can ask a question. And we have one actually here from Rob, and we'll get back to your initial question as well, Rob, just into Junli as well. So Rob says, Carlos, thanks for the nice tutorial and introduction on GAN methods for face generations. He says, I assume you want to generate these additional face images to increase the performance of your face detector or recognizer. Did you investigate the effect of the artifacts that the GANs introduce on the recognition performance?
Definitely, and I have to say that at the end of the project, already in 2020, the face recognition models had improved so much that actually we didn't need to use data augmentation to be able to recognize faces despite masks, despite sunglasses, despite these things. So in the end, it was not used. It was a very insightful exercise, and it was working very well, improving the accuracy of face recognition models back, those architectures that were existing already back in 2018, 19. But in 2020, 2021, the models have improved so much, and the data sets are available, are so good already and so diverse that really there is no need for that. Models are generic enough and work in very, very, very unconstrained environments.
Excellent. If anyone else has any other questions for Carlos, please keep them in. Oh, good one actually here from Edward, and then we'll go back to Rob's question for Junli. So Edward asks, do you think that GANs can be used in general for data augmentation when data is limited? He'd like to hear your thoughts.
Definitely. I think GANs are a very, very nice tool for generating data, synthetic data, especially if it's realistic enough. That's the problem. The main problem is to train the GANs so that they provide realistic results and they provide diverse enough results. Otherwise, we are having the problem of unimodality, and that can be even worse for training than not using anything at all. So try to use synthetic images for data augmentation whenever you actually need to. If you don't have the need, there is no point of doing it. But if really you have a very constrained, limited, or very biased data set, it's really, really a powerful technique. And especially nowadays, images are getting, the models are getting much better. Image synthesis is getting much, much more advanced than before, and it can really support to have a more consistent data set.
Excellent. Excellent. We'll go to the question for Junli, and then we get to your question now, Thomas. So Junli, Rob asks, is like, first off, nice intro into transformers. Yes, are there works that combine the idea of self-attention in transformers and unsupervised learning? It seems to be a concept of self-attention can be extremely useful for any form of semi or unsupervised learning.
That's a good point. I think these days it's a bit tricky to distinguish the self-supervised training or the unsupervised training. So self-supervised training, you don't require any labels. You try to learn as much as you can with the data itself. With unsupervised training, which is also trying to do this. So if we don't distinguish these two that much, this Dino paper that I mentioned is kind of in this line. After you train a good feature representation, then you can do clustering on top of it. You can use other unsupervised techniques on top of that as well. Yeah. Actually, Anthony, I have a question for Carlos.
Go ahead.
So it is very interesting, like using GAN to generate training samples. The one thing is, I think you touched on regarding the identity loss, which is that's a very important part that you try to keep the identity before, while you do the generation, you don't want to pollute that. I think, could you elaborate a little bit about how stable that is? I think these days people still having limited control regarding generating samples with GAN.
Yeah, definitely. Actually, that was one of the problems, how to control the level of, let's say, similar identity in the generated samples. And actually, it's a bit tricky because, of course, you are using a already trained model to control the identity loss that you're embedding into the GAN to generate samples that are similar in identity. So it's a bit of difficult to control that. And that was one of the problems that we had. In the end, not doing anything was working much better for face recognition models in particular. But I can foresee many, many tasks where generating data augmented samples with GANs can be very, very beneficial.
Thanks.
Excellent. And then look, another question for you, Carlos, as well from Thomas. He says, from time to time, symmetry left and right eye seems to be a hard task for GANs, and errors can be easily detected by humans. What can be done about it?
That's completely right, and especially in very, very unconstrained environments where you have very different sites in the faces, let's say, and a generated sample can become very, very artificial, very unrealistic, right? So, well, one can constrain that using an extra loss. Of course, you can use some kind of symmetry loss to try that the content in one side and the other is more or less the same. The problem always is to balance all these multiple losses. Then you are having a kind of card castle that you have to deal with, and whenever you touch one, the other one is getting affected. And let's be honest about that. Training GANs is not easy at all. There are many different approaches and suggestions that have been becoming part of the general know-how over the years. And right now, there is a lot of guidelines that you can find online. For instance, by the maintainers of PyTorch, they have provided a page of general guidelines on how to train GANs. It's really useful. I wish we had that 2 years ago, because it would have saved us a lot of time. But really, the problem is that it's actually difficult. You have to train the generator not faster than the discriminator. They have to learn at the same rate, otherwise one will eat the other and you will not successfully have the GAN well trained. So it's difficult, but usually the solution to all these kind of problems, little artifacts, little problems that you can imagine, is adding an extra loss that controls that specific part and try to weight it correctly with relation to the other losses, give the right importance. It's a difficult task, but it can be done most of the times.
Excellent, Carlos. Thank you for that. Any more final questions from anyone? Perfect. No, look, I think that will do it. And first off, look, thank you, Carlos. Thank you, Junli, for 2 fantastic presentations. I really enjoyed them, very technical. I know the content was good because I definitely didn't know what you were talking about, but mainly down to the engagement that you got after the conversations. But look, really well done. It's great to have you. Junli, great to have you part of the webinar again. And Carlos, great to have you here for the first time. If anyone's interested, feel free to reach out to Carlos and Junli on LinkedIn. I'm sure they won't mind. If you've got any other questions that you feel like weren't answered here, and look, hopefully it can all start to roll into a few in-person events, and we can all start to get to finally meet each other and meet the speakers and meet those who attend. But other than that, look, everyone have a fantastic week. Carlos, Junli, you've been fantastic. Thank you.
Thank you very much, Anthony.
Thank you.
See you around.
Bye.
Bye.